So, hello everyone. Welcome to another session of Coffee O'Clock. I'm your host Akash Kundu, and I am a PhD student at Institute of Theoretical and Applied Informatics, Polish Academy of Science. And today, as a guest speaker, we have Adam Glos, and he is also from the same institute, and he is an associate professor there. And at the same time, he's a researcher at Algorithmiq, where he is working with life science problems like variational quantum eigensolver and the related problems, optimization problems he's tackling there. And today he's going to give us an introduction to POVMs. These are kind of measurements and its application to variational quantum eigensolver, what he's working in currently at Algorithmiq. So thanks, Adam, and we are very pleased to have you within us. And it will be very helpful for us to learn from your experience and your research. So Adam, the stage is all yours. Please continue.
Thank you very much for this introduction, and also thank you for this opportunity to present some of mine and my colleagues from Algorithmiq recent results. Today's topic I would like to present is will be a rather light introduction to POVM, which is a generalization of measurements, plus some aspects of how this POVM can be useful in terms of variational quantum eigensolver or optimization in general. As Akash said, I am right now in both Algorithmiq, company Algorithmiq, and the Institute of Theoretical and Applied Informatics. Right now, these results were made by within my work made for Algorithmiq. So perhaps I guess we could go on with the topic, and we'll start very lightly. We'll start with how the classical world looks like. So imagine you have a machine for which we are giving a number. Suppose we are giving it always a number 0, and this machine is performing some stochastic operation, which finally gives us some probability distribution of numbers, say 0 to d-1, two possible numbers. This is how our classical, you could say, big scale world works like. But let us consider a very specific task. To suppose that we don't know exactly how this machine works, but we are interested in what is the probability distribution of the integers we are giving at the very end. So probability distribution over d possible states is defined by the vector of non-negative values which sums up to R. And any such d element vector has d-1 degrees of freedom. Why only d-1? Because if you specify the first d-2 elements of this vector, then it must hold that some of these probabilities must equal 1. This means that the very last element, the very last element can be computed as sum of all the other probabilities. How we could find out them? We can, for example, give many zeros to these machines, say a capital S number of them, and check how frequently each of these outcomes are appearing. With high probability, if we divide number of how many times the value I appears over the total number of shots, it will approximate the probability of getting the outcome I in general. What is important about this step is that independently on how this machine works, if it's giving some fixed probability distribution, then we can always find out what is the probability distribution using this method. Now let's see whether we have the same situation in the case of quantum computer. So in quantum computer, we start with some state. Let's say that the correspondence state for the 0 is ket 0. By the way, I can assume some basic understanding of quantum mechanics, right? What is ket 0, unitary matrix, etc. Okay, I take it as a yes. We change it through machine right now applies some unitary operation u, and we can again make a measurement. So suppose how you have a qubit, the most simple scenario. So in general, qubit can be written as a superposition of two basic states, 0 and 1. So alpha and beta are complex values. So initially we could think that this alpha, we have 4 real degrees of freedom. However, first of all, we need to make sure that this state is normalized, which effectively go to removes 1 degree of freedom. And secondly, there's a thing called a global phase, which says that if we have 2 states, psi and psi multiplied by exponent to minus I times some real number phi, these 2 states are physically indistinguishable, which effectively removes another degree of freedom. So with this, we can say that each qubit has only 2 degrees of freedom out of 4. However, this is still twice as many compared to the probability distribution, because for probability distribution, we have only 1 degree of freedom. What is the most basic, simple effect of this? If we perform the measurement in the z basis, so only in the z basis 0, 1, then because this gives us probability distribution, we can find out only 1 degree of freedom for this test. For example, if we take generalization to state with d basic states, which has 2d minus 1 degrees of freedom, we can easily find out that in this modulus of amplitude can be computed by square root of number of curations of j over s if we measure in computational basis. But then we lose all the information about the so-called local phase. Simply by measuring just with the computational basis, we cannot distinguish this. What we can do is that we can, for example, of course, apply, say, Hadamard's on the right before the measurement, which will give us the phases, but then we lose the amplitudes. So what I mean here is that by fixing one measurement, for one von Neumann measurement, we cannot learn fully all properties of the quantum state. Let me just clarify one thing. Of course, there is a concept of Heisenberg. Sorry, it's not Heisenberg. It's the uncertainty principle, where we say that we cannot get phase and amplitude simultaneously from one particle. But here I'm saying something a little bit different. That even if you have multiple copies of the quantum state, if we perform a fixed measurement in basis, we will not be able to learn fully the quantum state.
So, Adam, you mentioned something about changing to a different basis. Could you repeat that? The Hadamard basis. Yeah.
Yeah. So I mean, if we would gather some statistics from, okay, so maybe I should. You should mean that I should explain what I mean by this, right? By changing the basis. So, for example, imagine that we have a measurement device C, then probability of measuring 0 is equal to this. But the thing is that this 0 can be replaced with completely arbitrary state. For example, it can be replaced with the plus state. Plus state is the equal superposition of 0 and 1. We can also consider minus, it will be minus state. So how we can make this measurement? What we have to learn, we need to learn the unitary operator, which would transform 0, 1 into plus minus. One of such operators is Hadamard. So basically what we need to do is, despite having this measurements anyway needed, we need to apply the Hadamard type before. Because one way of seeing this is, traditionally we see that, okay, we have Hadamard which we need to apply to quantum state, but we can also use something which is called Heisenberg picture, which means that this Hadamard changes the detector, such as the basis in which we measure.
Right, thanks. And how does changing into the Hadamard basis allow us to get the phase information? Or did you?
So if
yeah, maybe we can take it.
I mean, I didn't want to focus too much on this, to be honest. But if we have this kind of state, it's just normalization here. Then we have 1 plus sorry. Because I need to square later. Plus this is 2. Sorry, very. So this is the overlap with some. Okay, this is quite special, I must say. State C and plus, right? This was the overlap. Now we are interested in the probability distribution of this. Note that C is some set of states, in fact, but only differs with this phase. So we can continue with this. And you can see that by changing this phi, we are changing the probability distribution. So if we can assume that this is uniform superposition, then basically this allows us to determine what is the phase phi in that case.
I see. So you using a controlled operation.
It's not controlled. It's just that you apply the Hadamard gate on this.
Okay. Yeah. Thanks. So I mean, if you remove all the math, then the main message is that if you measure in the Z basis, in the usual 0, 1 basis, then you can get the amplitudes. And if you change the basis into the X basis or the plus minus basis, you can also get the phase.
Yes. But these are two measurements, which what I mean that if you will stuck with only one of these two measurements, you will lose one property of the
one
state.
Or the other.
Exactly.
Awesome. So what you're trying to say is, in classical computing, you only needed one measurement to sort of, or one type of measurement to sort of get the entire data. But then in quantum, you need at least two different types of measurement to get the data.
Yes, actually even more than this. The thing gets complicated once you expand the dimensionality of the state. For qubits, 2 is enough. For 2 qubits, you need even more. That's the problem.
Right. How much would you need? You would need.
I think it's exponential, right?
I think it will be exponential. Yeah.
Awesome. Thanks.
Because each one gives you if you have d-dimensional state, then each measurement gives you at most 2 d-1 degrees of freedom. So maybe, sorry, maybe for quantums, for qubit, for pure state, maybe you are fine with 2 measurements. Yes. Okay, sorry. Here maybe enough. Sorry, because I was thinking the open system, so that's why I'm confused.
Okay, cool, awesome. But thanks. That I hope it's clear.
No problem. By the way, I really like to having questions in the meantime, so don't worry. That's me. Unfortunately, I don't see the chat, so if anyone could point me that there are some questions, I would be happy.
Yes. Yeah, don't worry about it.
Okay. So anyway, we have a fundamental question. If we fix a projective measurement into some basis, then we cannot fully understand the quantum state. And this is the problem which I will try to, in one way, solve today. How to make a measurement in a way that we can learn arbitrary property of the quantum state, whichever we want, which in a sense is equivalent to making a tomography on the quantum state. Why is it important to have this in particular? Is because in the VQE algorithm, maybe quick introduction. In VQE, we are having a quantum machine, which gives us a quantum state C, for which we compute energy E, and then we apply some classical processing, which changes the parameters of the circuit inside the circuit. Changes the parameter of the circuit. Sorry. The ultimate goal is to find such state C so that its energy with respect to some Hermitian operator H or Hamiltonian or observable, in a sense these are equivalent right now to me, will be minimized to this VQE. But to do so in VQE, we need to actually compute the measurement. So we need a well-defined measurement which computes this energy. And von Neumann energy, unfortunately, is already not enough, even for pure states. So anyway, my goal will be to show you how we, in particular, can describe a measurement so that we can compute energy of the arbitrary Hamiltonian. But before this, I will make things a little bit more complicated because I will introduce the concept of the open system world. So before, I was using something which probably most of you know, which is a pure state description, in which the state is simply a superposition with some complex amplitudes of basic states. Right? This is the most general description of the state which is in an isolated system. However, we could think of something like this. Suppose we have a few machines which maps ket0 state into some state C1 to Ck. We have K machines. We choose an appropriate machine with probability P1 to Pk. So what I mean here that we don't have really a quantum state as a vector, but we have some probability distribution over these quantum states. And the way we can describe this probability distribution of quantum state is the mixed state, which is exactly the formula which is in here. So we have sum with the probabilities of projectors on each state. In particular, if we have just one state, which we know for sure, it will be just state like this. And this, in fact, is the most general description of the quantum state, no matter what study would assume. Of course, assuming the quantum mechanics laws are correct. So at the moment, we only make this more complicated because we have an operator for which we can prove that its trace is 1 and all the eigenvalues are non-negative. But if we have d basic states, for quantum state, we have 2d minus 1 degrees of freedom. But in here, we have something around d squared. So our number of degrees of freedom only blow up. So we would need even more measurements. And this is actually where we would actually need exponentially many measurements. Exponential with number of qubits, of course. So this becomes very complicated. But we'll get to this later. What should we just remember from the slide is that this is the description of the quantum state, which I will use from now. I have a think that there are many questions in the chat.
Not yet. We're just like.
Okay.
Yeah. I'll let you know.
Okay, then I will wait for interruption. But of course, now, what we had before is that we have multiple machines. We put 0 to all of these machines, and we are receiving some state. But these machines can, in principle, accept many different quantum states, not only 0, because it's just some form of evolution of the quantum state. So imagine now that we have a general quantum state and we put to these machines at random. And they perform unitaries U1 to UN. Therefore, for the mixed state, now like in the sense of the matrix we had before, the resulting state will be of this form, like this sum. I should already said, this is not the most general description of the quantum channel. There are quantum channels which are not of this form. Still, these are quite frequently used even for modeling the noise on the machines. Anyway, I will not talk too much about quantum channels. What should be learned from this slide in turn is that unitary on a noisy system, which we have actually environment interactions, actually will look like a quantum channels, either of this or a more general form. And finally, we are coming to the most interesting part for this presentation, which is about the measurement. So in Wilde's book about quantum information theory, there's a beautiful explanation how we can derive this formulation of POVM. However, in here, I will already just use this as something known. Suppose that we have a machine which accepts a quantum state rho, performs a measurement and gives us some classical label M. Well, we could imagine some very strange procedure which would give us this M. For example, we can make unitary rho, apply some random unitary on it, and check the outcome. We can then relabel this. We can have very specific procedure which would allow us transforming the state rho into some outcome M. However, whatever procedure we would come up with, it can always be described, its probability distribution, with something which is called POVM. POVM is a set, maybe more familiar would be a function, which consists of matrices such that they are non-negative, meaning that all of the eigenvalues are non-negative, and furthermore, that they sum up to identity matrices. Why this is important, I will tell you in a minute. However, its effect on the quantum state is if we are given the quantum state rho, like in here, then we'll get probability outcome M with the probability given by this formula. So trace of rho times EM. Which is, again, this is the probability. And it can be shown that this is the most general description of the measurement you can imagine if you are not interested in the outcoming quantum state. This is the only assumption. So, why these two constraints are important? The first constraint is important to just make sure that this probability PM is non-negative. It's having negative or even complex probabilities would be strange, right? So, in particular, if we want to have it for general quantum state, we want to have it for general pure state using basic properties. This will be C, but this must hold for any psi, and this condition is equivalent to EM being non-negative. Furthermore, what we also want is that these probabilities will sum up to 1. And this I will not show precisely, but I will just show why this condition makes sense. Which is, if we take some of the probabilities, we inject the formula from the middle of the screen. We will use the linearity of the trace. EM. And since this is identity, this sum, this is trace rho, and trace of the mixed state is 1. This is something which I mentioned previously. Of course, this is not a formal proof, but this is just a brief explanation why it makes sense to have this kind of condition. In fact, since I said that this POVM describes a very general measurement procedure, we can also describe it this way: our typical computational basis measurement just by taking the projectors onto state M. One can quite easily verify that both of these requirements hold and that these probabilities will match. But the good thing is that we can go beyond this. In particular, the set of M can be arbitrarily big, which in particular allows us to have sufficiently many classical outcomes, in principle as many as there are degrees of freedom. So, of course, it's not that just presenting the measurement in this POVM will give us something which allows us to reconstruct the quantum state. Because in particular, having this von Neumann measurement description, we already know that this is not sufficient, right? For this, we need something which is called informationally complete POVM. What does informationally complete POVM mean? It means that, of course, it has sufficiently many outcomes, and in a sense, by definition, over the definition a little bit more formal, that all these dual effects spans the space of all mixed operators. Because this holds. Applying this many measurements on the fixed quantum state, multiple copies actually, allows us to approximate the quantum state itself. But this POVM can be, of course, very, very general. Part of its operators EM. If we have many qubits, it can be non-trivially acting on all the qubits. But we have actually a very nice property coming from the very definition of the tensor product, is that if on each qubit we have information complete POVM, then in fact POVM considered as acting on the all qubits simultaneously is also informationally complete. So it is enough to define good informationally complete POVM with 4 effects, because mixed state has on qubit has 4 degrees of freedom in turn. It is enough that as POVM 4 qubit, and then we can reconstruct the whole state, at least approximate. This way, having this 1 qubit IC-POVM, it is far more easier, at least in principle, to design such IC-POVM.
Adam, I didn't understand the difference in like POVM and like IC-POVM, because in POVM you cannot just reconstruct the state, but you can get the statistics, right?
POVM is something very, very general. Information complete POVM is a special type of POVM, so that if you have many measurement outcomes coming from this information complete POVM, you are in principle able to reconstruct the quantum state which we are putting.
Okay. So the structure of the IC-POVM information complete is different, right, from the POVM. It has something addition, right? Because
yes,
it tracks of the like local phase and stuff, right?
In particular, if you consider all the space of all negative operators, you can say that this FX EM okay, so this FX EM spans the space of all non-negative operators. So any non-negative operator can be formulated as the linear combination of these operators.
Right.
For one-dimensional measurement, this is not true, because, for example, if we consider operator 111, then there is no way that we can represent this as a linear combination of this effect, right?
Exactly.
So this is POVM, which is not informationally complete in particular.
Yeah, that's interesting. Yeah. Thanks.
Okay, so how we can implement these POVMs? Well, there are for sure multiple ways. I will present 2 of them, which were in particular considered in our company. One way is by expanding the size of the Hilbert space. This is because we need 4 outcomes, and since we need 4 outcomes, 2 qubits gives us at least spatial bits. And another way, which is a little bit more complicated, is by randomly choosing the basis of the Hamiltonian, and then optionally do something which we call relabeling. I will go explain this just in the next slides. So first, let us consider the dilation POVM. In here, we use a simplified version of the Neymark's theorem. Neymark's theorem essentially says this: if you have, I will tell a version for qubit, but it generalizes to more complex states. if you have state row and two ancillary qubits 0, then there is such unitary U and measurements acting only on these ancillary systems, such that this probability distribution will corresponds to the POVM you want to apply. You only need to apply, appropriately choose the unitary U in this circuit. Again, this is version for qubit. It's generalized to more complicated cases. In fact, we use a little bit simpler method, which uses one less ancilla. Is that instead of measuring, having two qubits as ancilla and measuring both of them, we have one ancilla, but we also measure the state which we want to understand. What is important is that this unitary operator cannot be completely arbitrary, because if you could imagine that there is, for example, X gate and you don't do anything on the second system, then you are not passing any portion, even tiniest portion of information from this system to this system, and this measurement will be completely irrelevant to row. So you will not be able to understand this. So in particular, you at the very, very least need at least one entangling gate, for example, CNOT.
So what I understand is that in previous methods, you needed same number of ancillas as the dimension of the state, right? To reconstruct the POVM. But right now, when you measure the state itself, then you need one less ancilla, right?
Yes, because you always need 2 bits for qubits, right?
Mm-hmm.
So instead of having these 2 bits from the ancillary qubits, you're taking 1 bit from this auxiliary qubit and 1 bit from measurement acting on the original system, exactly, or the original particle. So in a sense, it is like removing these 2 things. Yes. Of course, that way you cannot implement arbitrary POVM. However, this is still a very rich class of informationally complete POVM, so it is still very interesting.
But as you said, that this new dilation POVM, it has a constraint that it need to be connected, like the state and the ancilla. But in the previous case, if
exactly,
one of the ancilla is
must be,
yeah,
it also must be connected. There also may be some entangling gates which is acting between the row and both of these ancillary qubits.
I see. Okay.
Because the simple reason is that you simply need to pass some information to this auxiliary qubits. If you will not pass any information, you will hide this in row, then this measurement will be completely independent of what your state row is. So you get nothing interesting from this. But at least you need 1 qubit. This is a must-have, basically. And this is one way of doing things. But there is also another way, which is about resampling, randomized resampling. What we do is that, first of all, we choose with probability alpha 0 a measurement basis P0. A measurement basis can be understood in the way as we talked previously with this X basis, so that we apply some unitary U0 and then perform a measurement in computational basis. Then we obtain, sorry, give me a second because I didn't see some part of the presentation. Then I'm having outcomes 0 on 1. This is purely random because this is coming from the quantum machines. And optionally, but this is actually quite useful, we randomly change this outcome 0 or 1 into 1, 2, 0, 1, 2, 3 outcome. So that we always have 4 outcomes at the very end. If this measurement, this P0, are chosen appropriately, for example, they can be measurement in Z, X, and Y basis, Y Pauli basis, then we can, in principle, reconstruct the quantum state. What is the probability of getting outcome M? Well, first of all, we have the state row. You see the spotlight, right, at the bottom. Then we apply the unitary UI, which were sampled with some probability. We have, and this is also something, of course, something we cannot control because this is a quantum part. We apply the measurement of outcome J. And then, based on the which unitary we sampled and which outcome we get, we are relabeling the outcome from ij to m. So this whole formula gives us probability for a given state row of having the outcome m. In fact, from this formula, it is relatively easy to see how the effects will look like, and I will show these effects, but this will be in some of the next slides. So these are the two methods of how we can make a measurement which, if appropriately designed, will be informationally complete and will allow to reconstruct the state. So now let us consider again a single qubit. If we have state and we perform measurement in whatever fixed way we would imagine, then this state is transformed into a random variable which gives us some outcome m. As I said before, this outcome m, okay, this maybe I haven't said it before, but for information complete POVM, this outcome m can give us, and unfortunately I'm using again the same symbol, but now it is not effect, it's the energy with respect to the Hamiltonian. Maybe I should use some, I know what I will use. Let's make it symbol like this. So this is the energy coming from the energy portion you could think coming from the measurement m. So in particular, for S measurements, our estimates will have the following form. And this is some random variable x. But this is, if we forget about the quantum origins of this random variable, then we could consider this as a classical random variable from which we sample many times. Therefore, we can use the central limit theorem, and we can say that this for sufficiently many shots, this random variable x will behave like normal distribution with some mean me and variance sigma squared. In particular, this means that with the precision of the energy you estimate, this mean, will decrease with something which is proportional to 1 over square root of s, which is quite nice. We have relatively good energy approximation, but the problem is that this O notation can hide very, very large constant. This constant, which is in here, can even grow exponentially with the number of qubits, which in turn is pretty bad. But while for fixed POVM we cannot do anything better than C over square root of S for arbitrary state, we can in fact try to look for a better POVM, which still give us the square root of S decrease in precision, but with C with this constant, which is much smaller than the one which originally took. In case of dilation, for example, let me change the color. We can change, for example, the unitary operator. In case of this second approach of relabeling, we can change the probability distribution, which gives us some measurement. The form of the measurement itself, meaning in which basis we measure, and finally the probability, this conditional probability relabeling the outcome. As you can see on the right, we have much more degrees of freedom. And what we would expect that with if we, for every portion of shots, we increase, we improve the POVM, this information complete POVM, with the same number of shots, we'll use, we will have a better approximation of the energy of the quantum state.
So what I understand is that for each shot, you are getting some outcome M, and you are evaluating the energy, right?
Yes.
But as you are accumulating the shots more and more and more, then it is converging to the normal distribution.
Yes. And this mean energy, this variable x, let me pronounce spotlight. The variable x, which is the mean of all the energies, will behave like the normal distribution. This is precisely what I mean. With me being the true energy of the quantum state with respect to the observable.
Yeah, and then the energy decreases like the statistical error, right? 1 by square root of n, but it is like this O. And why this O is exponential? You said this constant. I didn't understand that.
Sorry?
Like this, you said this multiplicative constant because of O is exponential sometimes, right? Why is that? Could you please repeat once again?
This actually I haven't explained, and unfortunately I am not sure if I can explain this well at the moment. One possible explanation is coming from this uncertainty principle, I would say. That because we cannot measure, in a sense, actually, I'm not sure if I can give a good explanation at the moment. This is something which we for sure observe, this is something which is well known in the community, but I'm not sure if I can explain this, why this constant may be exponential in case of information complete POVM.
Okay.
For typically how this is done, this is because if you have this uncertainty principle, then you would need to have exponentially many different bases in order to compute the quantum state. However, and this is which was the problem in here. So I'm not sure if I can give the honest answer right now.
Okay, it's completely fine. I was also wondering that. I mean, initially I was thinking maybe the ancilla is equal to the number of states. That's why. But okay, so we have another question. Is that, I mean, if we forget about the POVM right now, what happens with the same picture, this energy evaluation, when we consider projective measurement for each shot? How it changes? This equation of this M, mean of M.
So you mean the equation which I have right below the title, this one?
Yeah, exactly.
So to clear my drawing, perhaps. Typically how this is done is that the observable is written as sum of Hamiltonians for which we can directly estimate the energy, and then each AI is following some will follow some. Sorry, it's not zero. It will follow some kind of some normal distribution. So we will have sum of normally distributed variables. One thing is that this number of HI in general may be exponential.
Okay, so in case of projective measurement as well, it also converts to the normal distribution, like individually.
Yes.
Okay.
I mean, yes, exactly. So, and POVM contains this projective measurement. So whatever is holding for one different is it's okay. Sorry, it actually a little bit depends on the projective measurement we are dealing with, because right now I was thinking about general technique which allows us to measure for arbitrary Hamiltonian. But for example, if we have Hamiltonian, which we know that it is of this form, so we know it's eigen decomposition.
Right.
And if we would measure in this basis, then we will have only single random variable, which will again follow this normal distribution.
I see.
However, the problem is that in real applications, we do not know this decomposition.
Exactly.
So in principle, we can make this, but this, okay, one thing is, of course, that we don't know this in practice. In fact, this is the problem itself we want to solve. And another thing that this measurement in this basis may be very, very complicated, because the fact that we have very simple, in big quotes again, very simple projective measure, very simple measurement because it's projective, it doesn't immediately mean that this is simple to implement.
Right. Exactly. Okay.
This is why usually people just do measurement in the in the X, Y basis. This is, I would say, the typical strategy. And this will still be projective.
Right.
Very special because it will be a product over qubits.
So yeah, so this is the advantage, right? Because in the case of POVM, we don't need to know the eigen decomposition of that. And
actually, we have some kind of a bit more. What we also have is that in our case, we will have unbiased energy estimation, meaning that well, formal definition of the unbiased function is that if we have some function of shots, and we expect it to approximate, say, energy E, then unbiased means that expectation value of E will be equal to expectation value of this function f. So this is like formal definition of being unbiased for a number. And this is a very desired property because some of the estimators are only convergent to the actual value, meaning that instead of this equality, we only have convergence with s going to infinity. But in this case, we don't know, or we have always some imprecision just coming for sure for the fact that one from the statistical thing, but another that we didn't simply converge with enough shots to have good approximation. This is actually something non-quantum. This is something related to the even classical probabilistic theory itself.
So okay. So in summary, in case of projective measurement, it would be same like converge to the normal distribution. I mean, if we know the eigen decomposition, right? Or else it would not be possible. Like in the case of projective.
Well, of course, there may be some kind of trade-off, right? It's not that this is a very discrete property, but typically for interesting Hamiltonian, it is assumed that it has its eigen decomposition is very difficult, and therefore this constant next to the square root of 1 over square root of s may be big.
So there is another question. Would it be correct to say that a POVM is just a projective measurement in a higher dimension space or something?
No, I mean I wouldn't. Okay, of course it depends.
For just intuition.
Could you repeat the question actually?
No, like would it be correct to say that the POVM is just a projective measurement in a higher dimension space?
Okay, so there may be few understanding of this, but let me present one which is correct. Okay, I'm actually writing this again. Because any POVM can be implemented like this. Right now, this is something more general than the zero state until there may be many qubits. Then in this measurement, this measure which is in here is projective, and this is of course larger Hilbert space. So in that sense, I fully agree.
I see.
This is very good. This is very good. Basically, this is the dilation theory which I showed just a moment ago.
Exactly.
But many POVMs can be written without this. So in a sense, POVM doesn't explicitly presents the way of how it should be formed per se. There will be many methods how to implement them. But since we can always do it like this, then in particular this. This is something similar like what happens for quantum channel, because any quantum channel can be represented as a unitary operator acting on bigger Hilbert space.
Exactly.
So there's a full correspondence in here.
Yeah. Okay, thanks. It was like nice explanation.
I'm not sure how much time do I have.
Yeah, you already passed your time, but you can. Yeah, you can.
Okay, so I will try to be very quick.
Yeah.
So basically, these are the results. I don't want to go very deep in the methods. I will just briefly say that some portion of shots we were choosing or we're optimizing the POVM, and while typically you will have something for this dotted line. In here, we can have some kind of scaling which is going in complexity, you can see way below of this. And this is both for the dilation, which is this, I think it's pink one, and no, dilation free, these are something, which is the green one. Of course, it's also nice that you will simply go ahead and below, but let me say it again. What's important that these lines are not parallel to this dotted line. So in a sense, we're breaking this 1 over square root of s complexity. Probably in practice at some point it will start to be parallel, but still we have much better constant than at least the one we initially used.
So what is this adapt means here?
Adapt is basically this optimization of the POVM.
Okay.
So for example, for dilation, it was changing this unitary in here. And here it was changing this probabilities, this projective measurement and resampling. By the way, we can also see that this duration performs much, This duration performs much better than this resampling. There are actually good arguments why it is so. Okay, so now very briefly, as I'm already ahead of my time, of course, this all works very nice in theory because we were assuming idealistic model, there was no noise, everything was perfect, but of course, in reality, we have noise, at least for the moment. And there are two approaches how we can, how this can be solved. So one way is that we can simply mitigate error, meaning that we can try to perform a better synod, perform better measurement, or somehow remove this effect of the noise. But another very interesting thing is that simply we should change the interpretation. Because POVM can describe completely arbitrary measurement procedure, of course, on the noisy computer, POVM will be different, but it will still be POVM. So what we can do is we can make a tomography on this POVM, or this measurement procedure, in order to determine the actual effects. Going again, unfortunately, very briefly, for example, for no dilation, of course, we assume that this mixed state, which we have as an input, is ideal because it's like a completely different problem than the one we consider. This resampling and sampling of this classical procedure is also done ideally. Unitary operation, well, this is done on quantum computer, so actually this will not be perfect, but 1-qubit gates are implemented quite nicely on the machines. This is not what caused the problem, but the native detector, the one which, for example, on Qiskit you do by applying this measure function, is actually quite noisy. With very high probability, 0 can be in fact measured as 1 and the opposite. How we can do this? We can make a tomography on this J. We can make this tomography on J, derive the actual noisy effect of J tilde, and just inject this into this original formula. This is based on, thanks to that, we can always know the probability of the measurement. We just need to put different input states to derive this. Something similar.
It sounds like you're trying to do the tomography of the device, right? Not like this.
Exactly.
Yeah.
Exactly. This is what we are trying to do.
This is interesting, yeah.
Similarly, we can do it for dilation, except in here we don't really want to assume that 2-qubit gates are done ideally, because actually 2-qubit gates are quite noisy compared to 1-qubit gates. So what we can do is that we can make tomography on the synod, which will be described by, I can remove the spotlight. We can make tomography on the synods appearing these unitaries, so that this whole unitary will be replaced with some channel lambda. And in this case, the effect plus the same of the detectors, of course. And this will give us the effects for the noisy machines. There's like some small detail. I don't want to derive this fully because it's like a few line derivation. In here, I simply choose completely arbitrary but orthonormal basis of the non-negative operators. Finally, I would say the most beautiful one is that instead of treating independently the native detector, the synod, we can just consider this whole POVM as a complete black box. We'll be completely not interested in what is happening inside, and simply directly from this true as expected effects derive the noisy one. Well, this sounds the most simple operation. However, the previous two are still nice because it also saves some shots done if we assume some typical noise model. This all thanks to the being information complete, that you have all the information. So just to quickly summarize this, we make an analysis on the noisy simulators. And it's, of course, if we don't do any corrections in this blue line, then we are getting very far from zero. Zero is the ground energy in this case. If we do the correction, but we do not adapt POVM, we again have this 1 over square root of S. 1 over square root of S convergence of the energy estimation. And finally, again, if we adapt, we can go way below whatever we have from the corrected but non-adapted POVM, non-optimized POVM. Okay, so that was this one was for the no dilation. Very similar effect we have for dilation. And finally, because I am really close to and actually, as you mentioned, I'm past the time for my presentation. Quick, what I believe would be the most important facts is that first, projective measurements, if we fix one of them, are not sufficient to fully understand the quantum state. What we need is actually this positive operator value measure, which is a complete description of whatever measurement you could design. After choosing the information complete POVM, the quality of the energies, thanks to the central limiter, and decreases, the estimation precision decreases like 1 over square root of S. The precision is better than quality in here. For some, possibly and usually big constant C, which fortunately we can optimize even in reasonably general noise happening in the device. Other some reasonable assumptions. Assumption we need, for example, is that the initial state is well prepared and the 1-qubit gates are implemented with high fidelity. This was all very quick. I guess also very interesting thing is what bibliography I used. In particular, Vatrot, but also Vita has a beautiful introduction to open quantum system, including this mixed state, quantum channels, POVM. I really recommend both Vatrot and Vilde. Both books are really great. And this results concerning this optimization of POVM can be found in my colleague's paper, Learning to Measure, Adaptive Informationally Complete Generalized Measurement for Quantum Algorithms. And in case of noise and reliability part, there's another paper, preprint actually, where we can also find some, which in a sense is a follow-up of this second paper. So thank you very much. And if there are still some questions, I would be happy to answer them.
Yeah, thank you, Adam, for the amazing presentation. It was really, it didn't even feel like it was an hour, you know. It was really interesting. So
happy to hear that.
Yeah, and so if you have any questions, you can unmute or you can just write in chat. But we also had, yeah, people are also saying like it was super interesting. And thank you, yeah. So okay, so I have one question, because in the plots you had this black line, which is basically you didn't do anything, right?
The black line is just to show, okay, so as I said, if you fix the POVM, then the energy estimation decreases like a constant over square root of n.
Right.
Square root of number of shots. And this, for whichever constant you choose, it will be parallel in this plot to this dotted black line. Maybe here it will, if here it looks better. The thing is that in this plot I chose this C quite arbitrary just to so that you see how this is decreasing. In fact, this blue dashed line is also some constant over square root of S, and there is an orange line which is also a constant over square root of S.
So what is this constant factor you got to reduce, because it was exponential previously, right?
This dotted one is, I mean, it will probably exponential number of qubits, but keep in mind that the number of qubits is fixed. This is against number of shots. So probably this dotted line will be higher and higher. Okay, maybe not dotted line, but like this area around the solid line, which is the estimation error, standard error. Sorry. Well, these dashed lines were computed based on the experiment, and the dotted one, as I said, it was chosen. If I remember it well, it is chosen as the geometric mean between constants computed from the orange and blue. So it was just so that it looks nice. There's nothing deep theoretically for this dotted line. It's basic. For visualization, it was just to show that these two dashed lines are parallel to this dotted line. This is basically what it was for. What is important is that these green and pink ones are not parallel. They are not parallel to this dotted line.
Exactly. This is important, yeah. And this is the advantage, right?
Exactly.
I mean, because I was thinking like you have something like previously you had O2 to the power n. Right now you have O2 to the power some x less than n, something like that. I don't know.
Sorry, can you repeat?
Because previously you had this constant, which is O2 to the power n, right? The dimension, exponential. But maybe I thought right now you have something like O maybe 2 to the power of something else, x, which is less than n.
Could be. The thing is, we didn't make this how this constant scales with number of qubits.
Exactly, yeah.
So it can be that this is, personally, I would guess that this is still exponential, but with smaller base. I just not sure if the typical case is 2 to the n or 4 to the n. For sure, this is exponential.
But anyway, this gives like better approximate to the ground state, right? Like the energy.
Yes.
Yeah.
In a sense, with the same number of shots. What I didn't tell you here is, of course, if you have this nice assumption that 1 qubit gates are very good, the zero state is very good, and all the noise happening in the detector and the CNOT tomography, then if you make this tomography once, and if noise is not changing, then you only have some constant resources spent on this tomography.
Right.
But if you want to have this full black box tomography, then remember that changing this parameter x of the POVM in principle required to recompute again the tomography, so you have some extra shot noise. And actually, this is why these previous models are important, because if you have fixed good understanding of this lambda, which is coming from the noise model you assume, and the measurement, then by changing the parameters of the POVM, you can, at least with some precision, predict what will be the POVMs.
Right.
So this is why these two methods, with tomography on CNOT and tomography on the detector machine, are useful.